are back again, right. So next is, so this phasor diagram is a very simple one for this system, right, for this system. So next is the stability phenomena. So stability is a condition of equilibrium between your opposing forces, right. So the mechanism by which your interconnected synchronous machines maintain your synchronism, just hold on. So the mechanism by which interconnected synchronous machines maintain synchronism with one another is through restoring forces, right, which act whenever there are forces tending to accelerate or decelerate one or more machines with respect to other machines, because all machines are swinging in unison, right. Therefore, the mechanism by which interconnected synchronous machines maintain synchronism with one another is through restoring forces which act whenever there are your forces tending to accelerate or decelerate one or more machines with respect to other machines, right. So let me clear it. Under steady state condition, there is equilibrium between the input mechanical torque and the output electrical torque of each machine, and the speed remains constant, right. Now if the system is perked up, right. Now if the system is perked up, that means some disturbance is there, this equilibrium is upset, right. This is very common phenomena resulting in acceleration or deceleration of the rotors of the machines according to the laws of motion of your rotating body, right. Now if one generator temporarily runs faster than another, right, the angular position of its rotor relative to that of the slower machine will advance, right. That means due to some disturbance or something, if it happens that if one generator temporarily runs faster than another, right, the angular position of its rotor, right, is to that of the slower machine will be advanced, right. So the resulting angular difference transfers part of the load from the slower machine to the fast machine, right. Just hold on, let me clear it. So what happened actually, that the resulting angular difference, right, your transfer part of the load from the slow machine to the fast machine. This you should keep it in mind for general knowledge, right. Depending on the power angle relationship, this tends to reduce the speed difference and hence the angular separation, right, because they have to balance each other. As long as they are not losing synchronism, right, it has to be balanced, right. So let me clear it. So the power angle relationship is highly or what you call is non-linear. This power, just hold on, the power angle relationship is highly non-linear. So beyond a certain limit, an increase in angular separation is accompanied by decrease in the power transfer. This actually increases the angular separation further and leads to instability, right. So power angle relationship is highly non-linear, you know that is a sine function, right, or for a large system many other non-linearities are involved. So beyond a certain limit, an increase in angular separation is accompanied by a decrease in power transfer. This increases the angular separation further and leads to instability, right. So for any given situation, the stability of the system depends on whether or not the deviations in angular position of the rotors result in sufficient restoring torques, right. Otherwise system will lose synchronism, right. So you have to see that stability depends on the whether or your what you call the stability of the system depends on whether or not the deviations in angular positions of the rotors result in sufficient restoring torque, right. So okay, just hold on, I am coming back to the next one, just hold on. So when a synchronous machine loses your synchronism or falls out of step with the rest of the system, the rotor runs at a higher or lower speed than the than that required to generate voltage at system frequency, right. So I mean, when a synchronous machine loses synchronism or falls out of step with the rest of the system, its rotor runs at either higher or lower speed than the required to generate voltage at system frequency, right. So, just hold on. Therefore, the slip between rotating just hold on. The slip between your rotating stator field, that is corresponding to system frequency, and the rotor field results in large fluctuation in the machine power output, right. Then current, right, and voltage. This causes the protection system to isolate the unstable machine from the system. That means the slip between your what you call rotating stator field and the rotor field result in large fluctuation in the machine power output, current and voltage. This causes the protection system to isolate the unstable machine from the rest of the system, right. Otherwise, whole system will become unstable. So, the loss of synchronism can occur between one machine and the rest of the system, or between group of machines. Anything can happen, right. So, in the later case, synchronism may be maintained within each group after its separation from the others, right. Suppose one group of machine is somewhere, another group of machine is somewhere, right. If synchronism is lost between these two groups, then it can be isolated, but machines which are in one group, they may not lose synchronism. That is the meaning. Now, this analogy, right. So, the analogy is how that regarding the falls out of step. Therefore, the synchronous machine operation of your what you call interconnected synchronous machine is in some ways analogous to, it is something like this, that the synchronous operation in interconnected synchronous machine is in some ways analogous to several cars speeding around a circular track while joined to each other by elastic links or rubber bands, right. Suppose in a circular path, suppose so many cars are moving and they are tied with your what you call elastic band or rubbers, right. So, that actually what happened, the cars represent the synchronous machine rotor, say, and the rubber bands are analogous to your transmission line, right. So, cars actually represent the synchronous machine rotor, and you assume rubber band basically say analogous to transmission line. Then, so when all the cars run side by side, right, when all the cars run side by side, the rubber bands remain intact, right, because all are actually it is moving like this, this all are, suppose this is car, this is another car, this is another car, all are moving, and this is your tied by rubber bands. I mean, so many are there, say, and this is one car, this is another, this is another. As long as they are moving, there is okay, it is stable, right. So, now question is that if force applied to one of the cars causes it to speed up temporarily. Suppose in one car, if you suppose this one you speed up like temporarily, then what will happen? The rubber bands connecting it to the other cars will will stretch, because if it moves little bit ahead, this rubber band or elastic band will stretch, right. This tends to slow down the faster car, right, because as it tends, this is moving little faster, so it will be your it slow down the faster car and speed up the other cars, and similarly other cars will be speed up, right. Therefore, a chain reaction results until all the cars runs at the same speed. So, actually this is an analogous to this, right. So, the synchronism, right. So, a chain reaction results until all the cars run at the same speed, right. Once again, if the pull on one of the rubber bands exceed, right, then what will happen is pull on one of the rubber bands exceed its strength, it will break, because rubber band or rubber, it has some maximum strength, and if it is more than that, it will break, and here also one repeated twice, right. So, one or more cars will pull away from the other cars. So, this is something like your analogous to a machine, synchronous machine fall out of step, and when all cars moving in a circular path tied by a rubber band or elastic band and moving, and one car speed up, how things are, right. And if little bit speed is increase of one car, then naturally the rubber band or this is an analogy, or elastic band will stretch up. So, faster car will slow down the speed, and slower car will pick up your little bit more speed, but finally they will come to the but which will less than the faster car, and finally they will come to the balance. But if the strength of the, and this rubber band actually equivalent to transmission line analogous to, and if the strength of the rubber band suddenly exceeds, then it will break. So that means in that that car will be out of all other your cars from this rotation when they are rotating together. This is the analogy. So that machine is falling out of step, right? This is analogous to that. This is I have taken from a book, right? With electric power systems, the change in electrical torque of a synchronous machine following a perturbation can be resolved into two components, right? These two components we will learn much later, not now, right? Right now I have written here that delta T is equal to Ts delta delta plus Td delta omega. This is equation 2, but this one we will learn at much later, right? All these things will derive, right? Synchronizing component, damping component, right? And all these things will derive at that your I mean after when the at the end of this synchronous machine part. So this will derive, but here I have just written because for the sake of continuity of this topic, right? So where Ts delta delta actually this is the component of torque change in phase with rotor angle. What is change in phase with rotor angle? This, right? So that we will see later. Perturbation delta and is your delta delta and is referred to as the synchronizing torque component. So component of torque change in phase with the rotor angle perturbation delta delta and is referred to as the synchronizing torque. This how it is in phase, and this then we will see later, we will derive that one, right? Similarly, that Td delta or your what omega, the component Ts is the synchronizing torque coefficient, we will derive later. Then Td delta omega, the component of torque in phase with speed deviation. Once we are saying that torque is in phase with delta, and this one is torque in phase with speed, what is that? We will see later, right? Delta omega, and is referred to as the damping torque component. Td is the damping torque coefficient, right? So these equations later we will see detailed derivation of this one at the end of this when it will synchronous machine model will be developed first. After that we will see that. So system stability depends on the existence of both components of torque, right, for each of the synchronous machine, right. So lack of sufficient synchronizing torque result in instability through an aperiodic drift in rotor angle. This will later will take an numericals, I hope, and at that time we will see. So lack of sufficient synchronizing torque result in instability through an aperiodic drift in rotor angle, right. On the other hand, lack of sufficient damping torque results in oscillatory instability, right. So it is used to it is usual to characterize the rotor angle stability phenomena in terms of the following two categories. One is small signal or small disturbance stability. This is A, right. So actually small signal stability is the ability of the power system to maintain synchronism under small disturbances. Such disturbances occur continuously on the system because of small variation in loads and generation, because loads are switch on switch off. Because of that, generation also continuously increase or decrease, right. The disturbances are considered sufficiently small for linearization of system equation to be permissible for purpose of analysis. For the small signal stability, we will assume that disturbance is very small, such that all these equations, whatever mathematical things will be derived, it can be linearized, right. And instability that may result can be of two forms. One is steady increase in rotor angle due to lack of sufficient synchronizing torque, right. Another is rotor oscillations of increasing amplitude due to lack of sufficient damping torque, right. So the nature of system response to small disturbances depends on a number of factors, including the initial operating condition, the transmission system strength, and the type of generator excitation controls are used. So this is on a number of factors actually, right. To a small disturbance thing, that is initial operating condition, the transmission system strength, and the type of generator excitation control used. Question is that this excitation controls of the synchronous machine, if time permits, something I will talk about the your excitation system, right. So just hold on. Next is synchronous machine theory and modeling, right. So, in this case your what you call that your just a schematic diagram is drawn for synchronous machine, right. Plus and dot convention, you will be knowing that one is current entering into the plane, another thing is it leaving the plane, right. So, this is just hold on. So, this is your ANS pole is there, this is rotor, and these are all your what you call, this is field winding, this is DC, because for synchronous generator field is DC. So, this is DC, this is the rotor, and suppose it is rotating in anti-clockwise direction, this is omega r, the angular speed, right. And this is your stator, this is, if this is A, this is A dash, if this is your B, then this is B dash, and if this is C, this is C dash, right. So, one is I told you one plus or dot, that current entering the plane or leaving the plane, right. And second thing is, and this is your along this we have, this is d axis and this is the direct axis, and this is your quadrature axis. So, quadrature is leading d axis by 90 degree, right. And machine rotation of the rotor direction is anti-clockwise, that is here given here, right. And here these are all armature winding, right. Armature winding, it is marked between stator and rotor, the air gap is there, it is uniform. So, this is air gap is there, this is your stator part, right, and this is I told you this is the rotor part, right. This is a schematic, and this is your different axes are there, axis of phase A, phase B, and your what you call that's phase C, right. This is axis of phase B, right. Similarly, axis of phase A and axis of phase C. So, just hold on, right. So, all this your what you call ABC, that is you know that 120 degree apart, right, mechanical 120 degree apart. So, this is a schematic diagram of 3-phase synchronous machine. So, armature and field structure, whatever schematic diagram it is shown, right, but that is armature windings usually operate at a voltage that is considerably higher than that of the field, and thus they require more space for insulation, right. They are also subject to high transient currents and must have adequate mechanical strength. Now, therefore, the normal practice is to have the armature on the stator, that is why armature is on the stator. The 3-phase windings of the armature are distributed 120 degree apart in space, right, so that with uniform rotation of the magnetic field, voltage is also displaced by 120 degree, right, in time phase, and will be produced in the windings, because the armature is subjected to a varying magnetic flux. The stator iron is built up of thin lamination to reduce eddy current losses. When carrying balanced 3-phase current, the armature will produce a magnetic field in the air gap of synchronous speed, that is your, this is the air gap, this is the air gap, here, right. So, that is your at the synchronous speed. The field produced by the direct current in the rotor winding, on the other hand, revolves with the rotor, right. Actually it is actually how they do it. This field actually is on the rotor, and you need DC supply, right, and the rotor is rotating. Suppose if it is a 2-pole machine and 50 Hz, that means this synchronous generator is rotating at a 3000 RPM, right, and this your what you call the DC supply, actually it comes from somewhere. So, this is a question to you, that the DC actually field is on the rotor. So, how actually from where this DC supply come, how they do design, how do they design this, right, because field is on the rotor, that means something must be there for supplying DC, which is also rotating with the rotor, right. So, this is a question to you, and you just find out how actually it is done, otherwise we will answer you in the forum, right, because DC is on the rotor and rotor is rotating at a speed of 3000 RPM for 50 Hz system, right. That means whole mechanism is rotating at such a high speed. So, what is the mechanism then, from where the DC supply comes? This is a question to you, right. So, field produced by the DC current in the rotor winding on the other hand revolves with the rotor, right. So, for production of a steady torque, the fields of stator and rotor must rotate at the same speed, right. So, the number of field poles is determined by the mechanical speed of the rotor and electric frequency of the what you call the stator currents, right. So, the synchronous speed is given by this, the synchronous speed we sometimes use ns also is equal to 120 f by pf, that right. When n is the speed in rpm and f is the frequency in hertz and pf is the number of field poles, right. So, if f is 50 hertz, right, and pf is 2, so it will be 3000 rpm, right. This is actually equation 3, not 1, right. I corrected here, this is equation 3 because previously equation 1 and 2 are there, right. So, there are two basic rotors structures used depending on the speed. Hydraulic turbine, particularly for hydro turbine, hydro generator, right, operate at low speed because they have many number of poles and hence a relatively large number of poles are required to produce the your rated frequency. So, for hydro generator number of poles are high because those generators rotate at a lower speed, right, maybe 750 rpm or 375 rpm like this, right. And a rotor with salient or projecting poles and concentrated windings is what you call better suited mechanically to these situations. Such rotors often have damper windings or armature in the form of copper or bars. This I believe you have studied for your synchronous machine. So, we will not go into detail of that. Our objective will be different, the dynamics and stability, right. So, copper or your brass rods embedded in the pole face. These bars were connected to endings to form short circuited windings similar to those of a squirrel cage induction motor, right. So, in this case a rotor with salient or projecting poles and concentrated windings is better suited mechanically to this situation. Such rotors often have damper windings or armature in the form of copper or brass rods embedded in the pole face. These bars are connected to endings to form short circuited windings similar to these of squirrel cage induction motor as shown in figure 2a. That means either here it is placed and they are all either they all are joined together or it is open also. This is your continuous damper and here it is non continuous damper because it is cut, it is not there, right. So, they are intended to damp out speed of your what you call speed oscillation, right. The damper windings may also be non continuous, being wound only about the pole pieces as shown in figure 2b. Only here it is there, but here no question of continuity, only here it is there. If you have studied machine design, I believe you have studied this, right. The space harmonics of the armature MMF, right, that is magnetomotive force, contribute to surface eddy current losses. Therefore, your pole faces of salient pole machines are usually laminated. These all pole faces you will find for salient pole phase machine, it is your laminated, right. So, this is a continuous damper and this is non-continuous damper, right. Now, steam and gas turbines on the other hand, they operate at high speed and their generators your what you call have round rotors, that is cylindrical type of rotors, right, made up of solid steel forgings. They have 2 or 4 field poles, generally 2 poles in power system we see, right, formed by distributed windings placed in slots milled in the solid rotor and held in place by steel wedges, right. They often do not have special damper windings, but the solid steel rotor actually offers paths for the eddy currents which have effects equivalent to armature current, right. Some manufacturers they provide for additional damping effects and negative sequence current capability by using metal wedges in the field winding slots as damper bars and interconnecting them to form a damper cage, right, or by providing separate copper rods underneath the wedges, right. So, figure 3 shows the rotor structure that we will see later. So, for salient pole machines that generally you are used for this your hydro generators, right, whereas the cylindrical type of rotor that is basically for the your thermal power plant, right, or your what you call that your steam turbine or gas turbines, but gas turbines are different operating principle than the steam turbines, and for salient pole it is basically used for hydro turbine, right. So next we will, so now rotor, your rotor structures are given, right. So this is your schematic your diagram, and this is rotor slot and windings. Everything is given here, right, but drawing is not uniform because I have drawn it by hand. So this, but nowhere here, nothing is marked here, but here there is one thing I have marked it here. This is actually OH, right, this is actually OH, this is the rotor surface, right, this is the rotor, this is your rotor surface, this is your damper winding, this is your damper winding, this is your field winding, this is the slot wall, right, this is rotor slot and winding. It is a full schematic one, and from here this is shown, this OH, rotor surface, damper winding, field winding and slot, right. So this is solid round rotor construction, that is for your for thermal power plant or gas turbines, a cylindrical rotor, right. Now eddy current, actually this is a shaft. So eddy current, this is the direction of flowing of the eddy currents in the your what you call, this is the current path for cylindrical rotor, this is for eddy current, right. And for, if you see damper or wedge current, this is your damper or shown by this thing, then rotor surface eddy current is shown here, then slot wall eddy currents are shown here, and this is the field current. So ultimately all these eddy currents you have to design the machine in such a fashion such that things will be minimized. Those you have studied for electrical, your what you call electrical machine courses, right. But our objective is something different. This is the just preliminary basic thing, whatever thing little bit we are giving, right. So this is the current path in a round rotor, your what you call in a round rotor for your synchronous generator, which is used cylindrical rotor type, which is used for thermal power plant or that is steam power plant or gas turbine. So this is different, your what you call your eddy current, your what you call how actually eddy current flows, which places, these are all marked, right. But field current, of course you have to be there, otherwise machine will never run, you need the field current, right, and field is DC. So machines with multiple pole pairs. So machine with more than one pair of field poles, one pair means two pole machine, if it is four pole machine, that I want to mean pair, right. We will have stator winding made up of a corresponding multiple set of coils. For purposes of analysis, it is convenient to consider only a single pair of poles and recognize that conditions associated with other pole pairs are identical to those for the pair under consideration. Therefore, in our study, in our course, we will only consider the two pole machine, that is one pole pair, right. Therefore, angles are normally measured in electrical radians or degrees. The angle covered by one pole pair is 2 pi radians or 360 electrical degrees, right. The relationship between angle theta in electrical units and the corresponding angle theta in mechanical unit, we know that theta electrical is equal to P by 2 theta m. So P by 2 theta m, this you know, right. If you have any doubt about this thing, another course I have recorded, that is fundamentals of electrical engineering. There for single phase AC circuit, the just beginning of that, this thing I have also, I think I have talked about this, right. So theta electrical is P by 2 theta m, right. So that means your mechanically, if you suppose it is a two pole machine, if you have, right. So if it is Pf is equal to 2, then theta e is equal to theta m, then mechanically it is theta m, and if one rotation, complete rotation is 360 degree, but you have four pole ns like this, although mechanically it will rotate your what you call 360 degree, but in that case electrically it will be just double, because at the time Pf will be 4 poles. So 2 theta m, if theta m is 360, then it will be double 2 theta m, right, 2 into 360. So next is your MMF waveforms. So this already also you have studied, but I have to start this thing, so that's why little bit we have taken. In practice, the armature windings and round rotor machine field windings are distributed in many slots, so that the resulting MMF and the flux waveforms have nearly sinusoidal space distribution, right. So in the case of a salient pole machine which have field windings concentrated at the poles, shaping of the pole faces is used to minimize harmonics in the flux produced, but in this course we will not study the harmonics, right. I assume that you have studied all these things. Our objective is dynamics and control, which will come later. So, first let us consider the MMF waveform due to the armature windings only. The MMF produced by current flowing in only one coil in phase A is illustrated in figure pi. I will show that, in which the cross section of the stator has been cut open and rolled out in order to develop a view of the MMF wave, right. So, this is your what you call this coil sides, and this is distance along periphery in electrical degrees, and this is my MMF, right, and this is the MMF wave formed due to a single coil. I mean, it is something like this, that if it is just showing in phase A, right, in which the cross section of the your stator has been cut open and rolled out in order to develop a view of the MMF wave. So, this is only just for one coil, just is shown that this is the MMF wave. So, if you add one, later we will see, if you add one after another, so it will be like a staircase. Finally, you have so many, so shapes look like a sinusoidal waveform, right. So, this is MMF waveform due to a your single coil, right. With this, thank you very much. We will be back again.